Now we return to the final plenary session event, the Technology Roundtable. It is my pleasure to introduce the moderator, Professor Jan Rabaey, who holds the Donald O. Peterson Distinguished Professorship at UC Berkeley. He is the scientific co-director of the Berkeley Wireless Research Center and the director of the FCRP Multi-Scale Systems Research Center. Professor Rabaey will give a brief overview of the panel and will introduce the panelists and the domain experts. So please join me in welcoming this distinguished group.
Good morning, and welcome to this very first ever ISSCC plenary panel. And in light of the keynote presentations this morning, I think it's more than fitting that this panel is called Where is the Next Factor X 10x Reduction in Energy Efficiency? We're going to look at some challenges and solutions. And to do so, I think we brought together some of the brightest minds in the field to help us to get some insights. Now, about 25 years ago, Gene France at Texas Instruments realized that when he was looking at the generations of microprocessor or DSPs he was designing, that there was a certain kind of arithmetic connected to it as well, which he called Gene's law. He realized actually that the energy efficiency per function, and whatever you call a function, was basically doubling every 18 months. And this has enabled an amazing set of factors. This has helped us to reduce the cost of data centers, has made it possible to put more functionality in your mobiles at a fixed form factor, and has enabled us to build the beautiful devices, the medical sensors you've seen this morning. The fact that we keep on increasing energy efficiency of our devices. Now, in order to go forward in the next decade, it is essential that we keep that scaling of energy operational active. If not, we might face some important challenges. Now, the problem is that it's not going to be easy. There's a set of factors that have worked for us over the last decades or so that seems to be kind of scattering a little bit around the edges. First of all, the impact of technology scaling and the reduction in capacitance hasn't really evolved, or is not evolving as fast anymore as it did in the past. Voltage scaling, another one of our things in our toolbox, has been limited by a set of factors, such as leakage, process variations, reliability issues, and noise. We managed to reduce waste in our circuits. More and more we got aware that waste is not something we're allowed to have. So this is pretty much under control, we guess. The other factor is that over the last 20 years, we introduced a wide variety of energy-efficient architectures. Talk about dynamic voltage scaling, talk about parallelism, and all this type of things. Today, most products are using this. And at the same time, if I look at the technology, at the devices world, I see there's no game-changing devices that are on the immediate horizon, or are they? So the key question that we have to ask ourselves is, if we want to make this industry move forward in the years to come, what is going to give us that next factor 10 in energy efficiency to basically come to us? So to help us answer this question, we only can bring the brightest minds together, and that's exactly what we did. In search for answers, we brought together a group of leaders and what I would call wizened luminaries in the field to give us help and present their insight in what might happen in the next 10 years. Now, you may realize that in this picture that I show you here, out of the 29 people on this picture, 17 got a Nobel Prize. Now, I don't think this has happened yet to this group, but maybe it will happen in the future. So anyhow, without further ado, I would like to introduce our first panelist, Dr. Jack Sun. Jack Sun is Vice President for Research and Development and CTO of TSMC in Taiwan. He received a PhD from the University of Illinois and held a number of senior management positions at IBM Research before joining TSMC. He is an IEEE Fellow. Jack?
Thank you, Itoh. Good morning, ladies and gentlemen. It is my pleasure and honor to be here to share some perspective on the subject. I'll focus on technology from the bottom up, and then we need to count on you. We have to work closely together to innovate and solve the problem. In terms of power reduction, we certainly can learn something from Mother Nature and get some inspiration from the amazing human brain. A state-of-the-art graphic chip on the right has about 3 billion logic transistors, and it consumes 200 watts. In contrast, a human brain has over about 100 billion neural cells, which is the equivalent of about 1 trillion transistors, and it only consumes 20 watts. So we have a long way to go to catch up when we compare silicon chip with the state-of-the-art, with the human brain, where density is performance. So let's make density and scaling our friend again with parallelism and lots of energy-efficient transistors. And also we have to look beyond simply just transistors. And in the future, we may also explore the mixed use of memory devices for logic operations as well. In addition to parallelism and multi-core with lots of cool and good enough transistors, we must also push for the Pareto optimum curve as in the energy performance space, as illustrated in this figure from a 2005 paper by Mark Howoritz. Let's not waste any energy above this curve. And as we move forward, digital CMOS chip performance will be measured by speed times density at a fixed power budget. On the process technology side, we have quite a lot of examples that we can use to reduce power. In addition to transistor scaling, which I will elaborate a bit later, we can use low voltage and high bandwidth, wide I/O, digitally assisted analog, green interconnect, and maybe optical in the future. And not to lose sight of packaging side. With micro and nano technologies, right now we can actually use silicon interposer and 3D chip stacking to further reduce the power. On the transistor front, we do have many innovations to enable constant power density scaling to below half a volt, going forward to 10 nanometer node and beyond. Before strand silicon and high-K metal gate, actually we were in a power runaway situation with constant field scaling. Going forward, new device structures, high mobility channel materials, and variability reduction are the key things to focus on. Here are some examples of the new transistor structures with super swing and low variability that allow us to scale VT and supply voltage further. FinFET or multi-gate device is an ideal structure with super swing, low junction leakage, and low variability due to multiple gate control and low doping in the channel. We reported 70 millivolt per decade swing in our FinFET paper at last year's IEDM. On the right, a junctionless transistor It's also capable of 66 millivolt per decade of swing. Industry and academia have also made great progress in 3.5 high mobility channel devices. An Intel paper in 2009 IEDM reported significant performance gain of indium gallium arsenide, quantum well FET over strained silicon devices at half a volt. There are still many challenges ahead, but the progress and momentum on high mobility transistors is excellent. We hope 3.5 on silicon can surpass silicon in the near future for CMOS applications. In summary, density is performance, and we must scale power supply voltage and use parallelism. New device structures and high mobility channel can extend CMOS scaling further to half a volt and beyond. And we can use many other technology features to reduce power. But most importantly, we need to collaborate closely among process, circuit, system architecture, and software to realize the rest of power reduction. And lastly, don't forget the Pareto optimum curve. Thank you.
Our next panelist is Dan Dobberpuhl. Dan needs very little introduction. He is truly a legend in the world of microprocessor design, currently retired, whatever that means in his case. He has worked before at the Digital Equipment Corporation, DEC, Broadcom, and Apple, with some influential startups in between, such as SciByte and PA Semi. Please welcome Dan Dobberpuhl.
Thanks for the kind words, Jan, and good morning, everyone. Happy to be here. I'm going to talk about power efficiency in digital devices, basically performance per watt. And one thing it's important to realize is because it's highly nonlinear, it's important to compare at equivalent operating points. So compare performance at a fixed amount of power or compare power at a fixed performance level. Okay? All right, where have we been and where are we going? We designers have been fortunate to have been on the receiving end of a 1 over k cubed improvement in performance per watt from the technology development for many generations. However, as has been mentioned a lot this morning, this has fallen off rapidly in the last few generations to the point where I would suggest that we're in the neighborhood of 1 over k or less right now. And this is because basically voltage scaling hasn't been done as aggressively as it was before for obvious reasons. Capacitance hasn't scaled as well. Leakage power has gone up. So, and bear in mind that it takes 1 over k squared just to meet the improvement in device density per generation. On the circuit side, we've done a lot and accomplished a lot over the last few generations, scaling a voltage even more aggressively than the technologists to a degree. We've incorporated clock and power gating, tuned multi-VT libraries, etc. But I think the low-hanging fruit has been picked here, and looking forward, it's going to be difficult to make significant advances from where we are now. Similarly, on the CAD front, I think the low-hanging fruit has been harvested. That's not to say that there aren't a lot of chips out there that couldn't benefit from the advanced techniques that are available. Not everybody is at state-of-the-art. But if you're at state-of-the-art, I think it's going to be tough to go further looking forward. On the architectural side, things like parallelism, improved algorithms, etc., we've made good progress. I think there's a tremendous opportunity here to go further going forward. Digging down a level to technology itself, as Jack and others mentioned, it's very important that we continue aggressive voltage scaling. It's difficult but necessary. We need an SRAM solution, either 8T cells or process tweaking or circuit configurations, but we have to have a solution at low voltage. We need improved VT control. I think we need adaptive body bias to compensate temperature and systematic variations in VT. We need reduced mismatch in VT across the chip, and obviously subthreshold slope optimization. Overall, we need to enhance device dynamics for low voltage operation. I would say that we need to achieve at least 1 over k and hopefully better per generation of performance efficiency. Looking at a few figures here, I've got a comparison of the signal noise margin of 8T cell versus 6T cell. You can see how compromised the 6T cell is as you reduce the voltage. Also, this graph doesn't show the effect of VT mismatch, which just absolutely tanks the 6T cell. So we need a solution for this going forward. On the right, I have some graphs which basically show the effect of sigma VT on leakage current for an SRAM. So for a Gaussian distribution of VTs that range from a sigma of 10 to 50 millivolts, we see that the power distribution of the SRAM or the power of the SRAM is dominated by basically the minus 2 sigma VT because of the exponential effect with leakage and VT. Here's a graph that shows basically delay versus VT and VDD. At 1 volt, not much effect. But again, for the same variation to 50 millivolts in sigma VT, we see down at 0.65 volts that the curves spread out dramatically and that the overall device shifts significantly to the slow side as a function of sigma VT. This is a chain of 25 simple inverters. On circuits in CAD, yes, we have. I think we have harvested the low-hanging fruit, but still we can move ahead. Improved analysis techniques to take into account statistical variations, I think, are necessary. Also, dynamic error detection and correction is probably an important part of the future. On the other side, analog-assisted digital is a term that Anantha has coined, basically adaptive voltages and frequencies, DC to DC converters for fine-grained control, and other kinds of parametric compensation. I would say on circuits in CAD, we should expect to get a 1.25x improvement per generation, which works out to k to the 0.6. And then on architecture and algorithms, I think there's our best opportunity. Power-focused algorithms, parallelism, but remember, parallelism requires a reduced VDD in order to be effective, so it goes together with the voltage. And then programmable versus hardwired. Hardwired can be very efficient. I think it's a good use of improved transistor density going forward, and I think maybe FPGA or some similar approach will be important to making that possible. Bottom line, architecture and algorithms, I think 1/k is reasonable. I think we could potentially do a whole lot better, depending on the application. So in summary, I think that multiplying these all together, 2.5x per generation is still possible, which would yield to a 10x improvement in 2.5 generations. Thanks very much.
Thank you, Ben. Our next panelist needs very little introduction again. Kyo Ito is a Hitachi fellow and has been a pioneer in the development of semiconductor memory. He was the lead for 8 DRAM generations and holds hundreds of patents in Japan as well as worldwide. I also have learned that he has visited more than 90 countries in the world. Kyo.
Good morning. I'll talk about a personal view as a memory designer for the power reduction in the next 5 years. Challenges and solutions are summarized here. To cope with variability issue, we need FD-SOI to reduce VT variation and on-chip voltage generators for the compensation. To develop low-voltage logic, we need dual VDD, dual VT logic with gate source reverse biasing. And to develop low-voltage SRAM cells, we need FD-SOI and repair. Then I'll briefly explain some of the solutions. As you can see on the left, FD-SOI MOSFETs have 2 types of practical structures, SOTB, that is a planar ultra-thin box, and FinFET. They enable low-voltage operation due to reducing the maximum variation in VT, delta VT max, inversely proportional proportional to the square root of MOSFET size LW. As you can see on the right, in the 32 nano generation, even the most advanced planar has a large VT variation. If FDSOI MOSFET is introduced in the 22 nano generation, they are drastically reduced. Even so, for the planar, they rapidly increase with further device scaling due to rapidly scaled down MOSFET size LW. In contrast, for FinFET, they are maintained to the same due to adjustable LW by means of double fin and scaling up of the height. Thus, FinFET will continue low voltage operations over the generation. To my knowledge, however, it is more difficult for FinFET to compensate for PVT variation because substrate back bias VBB is unavailable, thus calling for something new. Dual VDD, dual VT logic with gate source reverse biasing is exemplified by the upper bus driver comprising 0.5 volt high VT level shifter and 0.25 volt low VT CMOS inverter to drive a heavy capacitance of 3 picofarad. To achieve low power and high speed, the input of inverter is overdriven at 0.75 volt by the level shifter. For example, when PMOS is on, the speed is enhanced due to the negative gate voltage of minus 0.5 volts. And when it is off, subthreshold current is reduced due to the gate source reverse biasing. This is also the case for NMOS. When compared with the lower conventional 0.5 volt high VT CMOS driver, for a given delay, average current is almost halved at a halved power supply. Thus, power is reduced to 1/4. Note that necessary total channel width is also halved. For SRAM, leakage reduction is a key because subthreshold current, I-sub, dominates even the active current. As you can see on the left, a hypothetical 1 gigabit SRAM at 100 degrees Celsius consumes as large as 10 amperes at the 0.28 volt VT, and thus 10 watts at 1 volt usually used in the 32 nano generation. The current is reduced to 2 amperes if VT can be increased to 0.36 volt, and thus 1 watt, if power supply is reduced to 0.5 volt in the 22 nano generation. A possible problem, however, is resultant reduced voltage margin of the cell. Fortunately, FDSOI and repair reduce delta VT max, thus enabling 0.5 volt 22 nano 1 gigabit SRAM with static noise margin of 40 millivolt for the worst cell. This slide shows expected active power of 1 giga. For SRAM, power may be reduced to 1/10, as mentioned before. This is also the case for DRAM if power supply is reduced from existing 1.35 volt to 0.5 volt. Thank you for your attention.
Thank you, Dr. Itoh. It's my pleasure to introduce our next panelist, Philip Magershak. Philip is Vice President of Technology Research and Development at ST Microelectronics. He has been a leader in the space of design technology and methodology for quite a number of years. He received his PhD from the École Nationale Supérieure de Télécommunications in Paris and worked at Bell Labs in the US before joining ST Microelectronics. Please welcome Philip.
Thank you. Pleasure and honor to be here, and of course very intimidating. There's only about 3,000 people looking at me right now. And I'm also a bit intimidated because I took a much more conceptual approach to the presentation than my previous and next colleagues. But still, I can assure you that it is based on sound facts and physical effects. So my first chart is basically saying that if you think about it, when all of us are trying to design systems and chips, basically, if you look at the constraint that we have, this looks like this blue cloud here, and the main message I'm trying to pass is that this is a function of time. So time represents, for instance, for the user, the various use cases. So if you have a user that is using a cell phone, he may sometimes use it to make actual phone calls, but most of the time use it to do video encode or decode or web browsing. And of course, depending on these different use cases, the system has different power patterns. This time arrow may also be the environment. As an example, again, in the case of a cell phone, the RF signal may be subject to blockers or not, or the distance to the nearest base station may differ. Another obvious environment parameter that varies is temperature. And then finally, also you can consider this arrow of time as the device time. So the transistors themselves that are subject to usage are actually degrading over time. There is elaborate effects that I won't go into detail right now, like NBTI or hot carrier or TDDB, that actually make it such that over time the chip degrades and basically the VT goes up and the performance goes down. So this is basically all what we have to deal with. And the approach, I would argue, that we are taking or that we have taken so far to address this changing environment over time is actually the approach of over-design and over-margin. So basically what we do is since we are not able to model variability or uncertainty, we just take a worst case, and be it in a process voltage or temperature, or be it in the quality of service, we take basically guard bands and over-design. Obviously, this is detrimental to low power. The other approach that we take is the one of divide and conquer. So basically, we have the approach of dividing the system into sub-blocks, and with the rigid interfaces, the obvious one being impedance being 50 ohms is a kind of a given by God. Certainly this leads to a lot of over-design and margin. So the suggestion we'd like to make is the following, and we call that, by the way, sense and react. And that basically that is that over time at any particular point in time, the system should basically sense what's around itself in the environment, or should obviously sense what the user wants to do with it, and react accordingly, and obviously only spend the power needed and the performance needed to achieve what is actually required, instead of being ready to spend maximum performance where it is actually not required. So obvious solutions to this problem have to do with adaptive voltage scaling. This was mentioned before. Body biasing, both forward body biasing and backwards body biasing. Obvious examples have to do with bias currents, and others with clock and power gating. So basically what we are saying is we are considering this paradigm shift where instead of today's approach, which is very rigid and which is essentially top-down, mind you, it is very useful because as such it allows the system designer to work separately from the software designer, to work separately from the IC designer, to work separately from the silicon process designer, and therefore enabling concurrent design. The unfortunate consequence is it wastes both power and performance. And we claim that as soon as we enable this collaboration at all the levels that you see on the right hand side of this picture, then basically each block is able to negotiate, so to speak, its own specification with either its neighbor or its environment via this sense and react concept. Obvious examples have to do with rigid global clocks that, as we know over time, are moving more and more toward the globally asynchronous and still locally synchronous. And why not actually consider fully asynchronous even for the local blocks? So in the future, we believe, since I wasn't able to predict what the system would look like in 10 years, forgive me for taking this example, but we are getting close to launch. But this is actually very relevant to our discussion. Each subsystem is actually, hopefully in the future, going to be optimized versus its peers and its environment, and adaptive to both of them, as well as we will see, be based on the co-optimization between system and circuit and process. So let me take just a couple examples from this picture. One is the antenna and the power amplifier for the transmit stage. Obviously, those are in the past or have been designed separately, and the fact that you can actually design them together and co-optimize them and model them together is leading to a lot of savings in power and performance. Another reciprocal optimization is the antenna with the LNA for the RX stage. Another example that was used this morning by Samsung is the wide I/O example, where you will actually stack the memory, especially the DRAM, on top of a baseband processor, and thereby saving a lot of power by doing parallel I/Os instead of serial. And then my favorite on this chart is actually FDSOI planar, which is a perfect example of an optimization that spans all the way from process to circuit to system and potentially to software, because this is a technology, as was shown by the previous speakers, which enables very good performance at low voltage, which is the name of the game when you want to save dynamic power. But also it enables very high performance once you use forward body bias, or it can pretty much shuts itself down in terms of leakage when you do reverse body bias. And all of this can be and must be controlled from the system level at the software level. So, of course, the main challenge with making this picture of co-optimization a reality is the design tools. And there are many design challenges. One of them is design for test and auto test and BIST. Others have to do with thermal effects modeling, mechanical modeling, electromagnetic, and so on and so forth. So in my last chart, I'd like to leave you with a picture of the future design flow that we need to make that happen. Basically, what this is at the center is actually a picture of a paper that will be presented tomorrow morning by an ST and LETI team, which is a 60 gigahertz RX and TX and antenna submodule. And basically, the way this was designed was, let's say, even though there is some adaptivity to the system, there is still a lot of traditional aspects. But let's just use this as an example. So you have on the top left of this picture the application constraints. You have the package boards, parasitics, and the manufacturing constraints. On the bottom left here, you have the power management, which is both obviously necessary, but also has to be co-optimized with the chip itself. The process variability, we have seen that in the previous speakers' presentations. Aging of the transistors and of the process, and then finally sensing the environment in this sense and react paradigm. So in order for this picture to become real, obviously what we need is many ingredients. The main one I'd like to single out is models of the process, model of the environment, model of the application, model of the use cases. This is a big challenge, but certainly collaboration will help us to make it happen. And this is actually necessary to remove all the chip and design margins that I was mentioning at the beginning, and basically, which is also enabled by the fact that this chip and system is constantly monitoring its environment. So the Holy Grail that we're aiming for is that the system only spends power and energy when needed. And definitely this is not possible with the current tools that we're all using today, as shown in this picture. I don't know about you guys. But certainly what we need is the next generation of tools and methods. And this is shown in this picture as the design seat for the low-power designers of the future. As a side effect, as we all know, it is difficult to entice young people to actually go to engineering. And I think if we show them pictures like this, we have a better chance. So this is a good side effect. But to be more serious, certainly we need very elaborate tools and very complex systems and models. But this is what is needed to get to the next 10x in low power reduction. Thank you.
Thank you, Philip. Let me now welcome to the stage one of the true leaders in innovative RF design, Professor Assad Abidi. Assad is professor of electrical engineering at UCLA and received his PhD from a good school, UC Berkeley. He's an IEEE fellow, as well as a member of the National Academy of Engineering. He was also the first dean of Lahore University of Management Science School of Science and Engineering in Pakistan. Assad.
Thank you. Well, this is perhaps the most challenging of the presentations. How do you cut down power of RF circuits by 10 times when power seems to refuse to go down? Well, obviously it'll require radical changes to the way we do things. In the receive side, the main trade-off is between low noise and high linearity. We want to receive small signals in the presence of large unwanted signals. So let's look at some fundamentals here. If we're after low noise at radio frequencies, achieving that in active transistors is always a high power proposition because they have to provide low noise resistance or high transconductance at high FT because they're dealing with radio frequencies. And that implies a large bias current. Therefore, to overcome this, it would seem that we have to use passive transistors to handle the radio frequency signals at minimum feature size, and therefore they'll be carrying zero bias current. They'll have low on resistance, which implies low noise. At baseband, however, low noise comes at lower currents. We can achieve high transconductances at low FTs where our signal now resides close to DC, and we can bias transistors in moderate to weak inversion. High linearity requires that we suppress unwanted adjacent channels as soon as possible and never allow them to build up voltages that might drive transistors into distortion. And finally, we have to remove the 50 ohm constraint that is a source of power waste. So a receiver front-end circuit of the future may look something like this. An antenna that goes straight into switches, FET switches, which are passive mixers, with no SAW filters and no need for a 50 ohm termination. And the signal of interest is down-converted, very close to DC or to DC, into a complex waveform. And then we have very low power signal processing through, for example, op-amps, with filtering applied immediately from there onwards. So this could bring about 3 to 5x lowering of power consumption because we've eliminated many of those RF front-end circuits. We also have to deal with the transmitter. Here the main trade-off is between high power conversion efficiency and linearity. The key to making good transmitters of the future is fast FET switches, and they could be used in something like a Class D type power amplifier for high efficiency. So we could have fixed voltage sources here and these fast switches that are turning on and off at the radio frequency, commutating the voltage across a floating load and going directly to the antenna. This would be highly efficient, and if the phases of these switches are driven by a simple outphasing scheme which could be implemented all in the digital domain, where phase modulation is imposed on an oscillator, and then taps are taking off delay lines in an advanced and retarded phase like this, we can exactly reconstruct any modulation. To get high powers out, we cannot use MOSFETs any longer because these fast switches also cannot support large voltages, and I think we will have to rely upon non-MOSFET switches such as gallium nitride, which could be deposited on silicon, or a very important alternative is the system in a package thing that we've seen in earlier talks today. The oscillator is the final RF component. That's never going to go away. For a given performance, its power consumption depends inversely on the inductor quality factor. So future technologies must provide low-loss, high-quality factor inductors and transformers either on chip or in the package where we have vias and bumps to connect to the thick film inductors, which could be very high Q with very low parasitic inductance. We also will need to tune these oscillators over wide ranges, low-loss RF switches, but they come from technology downscaling anyway. Finally, we must not neglect the low-power protocols that can sometimes bring about greater power savings than all the circuit improvements combined. An existence proof is the protocols developed for wireless paging, which allow a paging receiver to operate off a single small battery for a year or more. This will require elaborate power down modes and baseband, even transmission and communication protocols to be changed and become power sensitive. Adaptive circuits used widely in the receiver and transmitter that respond to the instantaneous bandwidth needs and the interference environment, very much in keeping with the last speaker's point about sense and react. And algorithm-aware, low-power, baseband communication, signal processing, perhaps network-on-chip concepts using highly optimized baseband blocks like FFTs and so on for the job at hand. That could bring dramatic power reductions over where we are today. All these things together, I think, can probably bring us to the 10 times reduction in 5 years that we seek. Thank you.
Thank you, Assad, for your insights. Last but not least, I would like to introduce Professor Hermann Oil, who just recently, very recently actually, became president of a newly formed group at Intel, which is called Intel Mobile Communications. Before that, he was connected with Infineon, where he was a member of the management board and served in multiple management functions before that. He also was a faculty member at the University of Hanover and a manager at Siemens AG before that. Hermann.
Thank you so much. Yes, you said last but not least. Some people say the devil catches the hindmost. So let me see whether I can deliver you something and you make the choice. And most of it already has been explained before. Hopefully not everything has been preempted. Let's go to this one here, the blue one at the bottom. That is the technology deliverables. We see that starting at the early days of GSM and now approaching towards LTE, we have, due to technology, about a factor of 200 of improvement of power consumption and power efficiency. So the remaining factor of 10 for the future seems to be hopefully achievable. But on the red one, we see that the speed has changed. About with the advent of the UMTS, but latest with the HSDPA generation, the demand for data rates is going up, dramatically is going up. This is good for us as customers, because this delivers fancy, cool gadgets every half year, every year. It's also good for the industry that provides this. So that is, in that way, a virtuous cycle. But there's also a vicious cycle, and this is for us as engineers, because this imposes even more demand, even more requirements on that what we do. And that's not all. All we know, these devices are portable. Portable devices interface to the physical world. And interfacing to the physical world means we have to have analog outputs and inputs. Mixed signal designs, analog designs, RF designs, we all know they don't shrink as nicely as digital circuits do. So, shall we give up? I think engineers tend to never give up. So what can we do? One thing is, of course, we can pick up the idea of algorithms and architectures and see that we can push analog circuits towards designs that shrink like digital circuits. This is good because then at least we would be rid of the disadvantage. What can we do more? And this brings me back to one of my early mentors. He always said, hey guy, the cheapest transistor is that transistor which you can avoid. Translate this into power consumption. The most power effective transistor is that transistor which is not there. So, what does that mean? Let me go to an RF transceiver. We know that this is one of the higher power sinks in a mobile device. And if we now look at this borderline here, everything at the left is digital, the right part is analog. And we are well aware of these designs. They have driven the technology for many, many years now. Following the principles, the first one is we push the envelope of the digital part closer to the antenna, and everything which is now at the left side of this demarcation line, that is going to shrink as digital circuits shrink, and maybe quite as important, this is programmable. We can change it. This delivers much more flexibility to the circuits. And with these merits, we can build transceivers that are more flexible, that can adapt more to different frequencies and demands. And having said this, it is possible to remove, for example, driver stages for different frequencies, power amplifiers for different frequencies, and we know it is about 5, up to 5 in today's 3G handset, down to 1 only. This is good, saves cost, that saves power consumption, and of course, it saves space. Too good to be true? Nice theory? I don't think so. Even within a time span of 2 years, with this technology, it was possible to reduce the power consumption, which was 2 years before, in average 190 milliamps, to 95, which is more or less 50%. So the power consumption could be pushed down by 50%. And as you can see at the bottom of this picture, also the real estate on the printed circuit board could be dramatically reduced. This is advantages for having smaller gadgets, or it frees up space for additional silicon, which brings more cool things into the gadgets. Whatever you use it for, this is good. And on top of this, it of course eases the requirements for shielding, and this delivers another cost saving. Having said this, altogether, I think what we know is that if we do evolutions in power efficiency, we see that the devices evolve as well. But if we are able to provide revolutions in power efficiency, we can also build the ground for revolutions in communication technology. It's your choice whether that what I presented was an evolution or revolution. It contributes. Overall, having said flexibility, software-defined RF circuits and analog mixed signal functionality enables power and cost savings beyond the semiconductor technology scaling. Thank you so much.
All right, there you have it. I think from our panel we learned a whole set of techniques ranging from the technology to the circuit system level that may help us to get that factor 10x over the next 5 years. Now, to make sure that we keep our panel grounded and check some of the reality of what they have proposed here, what we did is kind of pseudo-randomly select some people in the audience, or actually people who are domain experts who basically shown to basically ask some questions to our panelists and figure out if their statements basically kind of get some more insight in their statements. So I would like to start with Professor Mark Howoritz, who is a professor at Stanford University and also a renowned industrial pioneer. Mark.
Thank you very much. I have a question for Dan Dobberpuhl. It's a two-part question. In your talk, you described technology and architecture as being the major ways of getting energy efficiency. So the technology side is going to rely on voltage scaling. As somebody who's built a lot of very complicated circuits and how to put them in production, I'm curious in your view on how low VDD scaling can go and how well we really can use these adaptive loops that people are talking about given the mismatches that you see in real devices. And the second part is that I agree from an architecture side, there's a lot of advantages there. The problem is how do you put the customizations in? Because when you do that, you typically shrink the market, and that just increases design costs. So I'd be interested in your opinion on both.
Okay, thanks, Mark. Regarding the variability and adaptive VDD, at PA Semi, we did do an adaptive VDD control in 65 nanometer chips, and it worked reasonably well. We definitely had to add margin to the parametric controllers in order to compensate for the on-chip variation. Even though we tried to include it in the parametric controller, there was margin that had to be added. And so reducing the variability is definitely important to improving the efficiency of the adaptive control. But I think it's been demonstrated to work, and it'll get better. I think one of the other good things is that all the device architectures that people are talking about are targeting reduced variation in the devices. Everybody understands that that's a real problem at low voltages. So I think whether it's FDSOI or FinFETs or I'm even aware of work that's being done on planar bulk to reduce variability, I think we'll get there. Regarding the question of the hardwired circuits versus programmable and the constraining of its application and the cost of development, necessity is the mother, and I think that the necessity will drive it forward. I think that IP providers will find a range of opportunities going forward for this due to the advantages of the power. One of the areas that's definitely a problem with hardwired IP is validation. That's where I think the embedded FPGA or something similar may be important, because I think maybe the control logic ought to be designed in a way that is amenable to field ECOs, because we know that validation of control logic is especially difficult.
Thanks, Dan. Another one of our distinguished question askers is Professor Takayasu Sakurai, who was the recipient of last year's DOP medal, and he's going to phrase a question, I believe, to Jack-san.
So, Jack, I totally agree with you that it's very important to have a collaboration in between the systems and circuits and devices. Recently, low-power circuit designers use adaptive VT and adaptive VDD to pursue a low power under VTH variability. And the future of those controllability of VTH and VDD depend on the choice of a MOSFET device structure and technology in general. So as a forerunner of the CMOS technology, could you give a comment on the future of VTH and VDD controllability? If in the future it becomes very difficult on the design side, could you give a comment on the control of the within die and die-to-die VTH variation, which may hinder the realization of power-efficient LSIs?
Thank you. Those are excellent questions. From transistor design standpoint, transistor structure standpoint, whenever I discuss this with our manufacturing folks, they always say, give us the best architected device design or the transistor. So that, because our manufacturing folks, they think they can really do the die-to-die in the manufacturing control very well. That's what they are paid for. And so it comes back to what kind of a transistor structures that intrinsically gives you the lowest variability. And I showed one example of FinFET. And because of the multiple gate control, and we have already seen, and also some reported data, that from mismatch AVT standpoint, you can go way below 1 millivolt micron in the 0.5 regime. So as long as we can scale the sigma VT, you don't have to worry too much about the variability. Of course, there's still a lot of hard and grunt work that on the processing side to control the variability. And it goes without saying that we do have to work very closely together to use all the innovations, all the circuit tricks to help cover where process may not be able to provide sort of ideal situation. Thank you.
Dr. Ito, you might have some thoughts on that as well.
It's a very tough question. My talk was based on some new MOSFET, FDSOI, especially planar or FinFET. So as I mentioned before, planar FDSOI is maybe cheaper, and VBB is applicable to controllability, while FinFET has an advantage of reduced BT variation, as I mentioned, but it's a no application applicable. VBB is not applicable. This is a problem. So they have pros and cons.
Yeah. Right. Thank you. So to show that technology doesn't stand for anything, we actually also have some overseas question askers. So the next question will come from Hugo DeMan, who is Emeriti faculty at Catholic University of Leuven, also vice president of imec. So, Hugo.
In his concluding slide, Hermann Oil suggests that further savings in power will have to come from more software functionality. But so far, software programmability has always led to a higher power dissipation than dedicated hardware solutions due to considerable power lost into memory transfers. So, Hermann, can you suggest a number of techniques that will make these future software programmable architectures at least as power efficient as dedicated hardware? Thank you.
Yeah, thank you very much for this question from overseas, and which is actually closer to my home than the site here. And so, of course, if it is highly intensively asking for numerical processing, I would always suggest to stick to the old ground rule: compute local and control central. But I think what I've presented here does not go as far as that it needs real-time processing. This is more about either reconfiguration, or it is about changing the circuit tree on a much, much lower frequency. For example, when a handover is to be done between a GSM and UMTS call, or between a 3G and a 4G call in the future. And this does not occur so many times. So in that sense, it always makes good sense to stick to the old ground rules as you described them. And that is what we do in these transceivers. While on the other hand, we clearly see the flexibility contributes significantly.
Thanks, Hermann. I think that Mark has another question.
So this question is for Assad, and it's sort of follow-on Hugo's question, which is, I'm just curious, give me some specific numbers on how the power dissipation of the front end, like the LNA and the PA of an RF system scale with technology when active, for hitting the same spec. And you suggest taking out of the LNA, but I wonder about the noise performance there, so some comments on that. And then, as Hugo suggested, it seemed to me in the analog side, too, specialization has advantages. The passive components don't dissipate any energy and provide a lot of advantages in the front end. So in that regard, do you think the programmability and sort of making these general architectures like you suggest are really going to save energy, or will we be better off having independent front ends for the different radios that we need to build?
Thank you.
So I think there's sort of an intricate relationship between flexibility and the simplifications it brings and the overhead that flexibility might need. I think one way to judge it is by industry trends, and we just learned from Intel how they are going towards these more flexible architectures. And in fact, the large mobile device makers are all now reaching the limits of how much specialized hardware per communication standard they can pack in. So I think there is an urge and a need and hitting limits on where optimized solutions can take you. I think what people are discovering is that once you master the flexible software-defined kind of concept and bring about the necessary changes in circuits and architectures, you come out about the same if you use the similar kinds of circuits. And what I'm proposing is some radical departures from there to cut down power further, combined across many different blocks.
Thank you, Assad. Sakurai-sensei, you have another question?
My question is addressed to Itoh-san. I know that you are a memory expert, and you showed a very interesting approaches today for low power. Now, much R&D efforts have been put in the area of new type of non-volatile memory elements, like RRAM, MRAM, or PRAM, which may have a meaning in the realization of low power logic and memory. So could you give comments on the expectations and issues of the new type of non-volatile elements in the context of next 10x power reduction?
How long can I spend?
3 minutes.
3 minutes. Too long. Yes, no doubt, such emerging non-volatile memories are attractive because they might change existing memory hierarchy and provide unique and compact memory subsystem for PCs and mobile equipment. However, they must keep up with rapidly scaled down SRAM and DRAM, especially paying attention to the cell size and write endurance. To my knowledge, when compared with SRAM and DRAM, their cell size is still large, not competitive. But the power dissipation is almost comparable, thus enabling to reduce the power to 1/10 as SRAM and DRAM. And insufficient endurance, if any, will make memory system design complicated. Anyway, each non-volatile memory has pros and cons. So, considering current status of their R&D, I think we must carefully watch their rapid progress. Too early to say about it. Meanwhile, the alternative could be DRAM. This is because, in addition to active power, standby power would be reduced to 1/10 if FD-SOI DRAM cell is used. As you know, FD-SOI DRAM cell may extend the data retention time by more than 1 order of magnitude due to its extremely low p-n junction leakage in the cell. This implies battery-backed backup DRAM in the standby mode, and even battery over DRAM would be realistic. This is my comment.
Thank you. So we have one more question. I think it's the mother of all questions, and once again, it's coming from overseas.
So here's a question for Philip. For many years, the paradigm of complexity management has been the separation of concerns. But now you suggest that further power savings must come from a global optimization all the way from systems down to atoms. That sounds great, but as you state yourself, it will require a huge effort in CAD tool development, and that must optimize over all levels of abstraction, covering thousands of use cases and coping with the extreme variability of 32-nanometer technology. So, who will pay actually for the huge development costs of these tools that seemingly are only limited to a restricted application area? Will there be enough return of investment for the rather small CAE industry in the hypothesis that they have all the skilled system people in-house? Or will it lead to a revival of expensive in-house tool development? Thank you.
Thank you for this question. So the short answer is the EDA industry is about $5-6 billion revenue per year. If you add that up to, of course, the video game industry, which I just described, which is $15 billion, then that's a big amount of money to pour into solving this issue. But more seriously, it's a case of whether we will enable Moore's law to continue to happen, and as well as all the differentiated technologies. As we have seen in the case of the presentation from Samsung or TSMC or Toshiba, there is no doubt that we will go to 14, 15 nanometer, and then 10, 11 nanometer, then 7 nanometer. And in order to make use of all the transistors that are enabled by these technologies, there's no question that a much more holistic type of design solution is required, such as the one I alluded to, and which, of course, will require a lot of effort. So the way that progress has been done in EDA has been by leaps and bounds. We have had cases where academia, and namely, as an example, Berkeley has invented pretty much logic synthesis, and we know that this has become a major breakthrough in productivity and is now pretty much run-of-the-mill and is used in all the digital designs in the whole world. And there are cases where actually the bigger EDA vendors have introduced themselves some breakthroughs. And even though there is less venture capital going into startups in EDA than there used to, there are still some of them that are existing and surviving out there. So I think for all these reasons, there is the potential to make the development for the right solutions. This will not happen unless there is a very, very tight collaboration with the user side, obviously, all the way from the system and the software side to the circuit designers and to the process developers and the modelers of the processes. This has been the case successfully with 32 nano, 28 nano right now with the advent of high-k metal gate and the advent of variability that is associated to that, even though better than silicon nitride. This is also the case right now in 20 nano where we have to go to dual patterning. But certainly we believe that collaboration will be even more key in the system space. And collaboration and progress is actually predicated on the existence of standards. So the first, let's say, task that behooves all of us is actually to define the standards that are needed to make this paradigm shift happen. As reminders, when we moved from register transfer level to transaction level, we invented this standard called System C, TLM, and this is what has enabled this great move in productivity. Now we need to sit down together and come up with the standards that will enable the low-power modeling and sense and react approach at all the levels of abstraction that we described. So I'm optimistic, and we have seen that in the past we have been able to succeed. The answer to success will be through very, very strong collaboration. And despite or thanks to collaboration, there will still be a lot of room for competition and differentiation. And at the end of the day, we will reach the 10x low power thanks to this next paradigm shift. Thank you.
Thank you, Philip. So we're approaching the end of the panel, but before closing, I would like to go around the panelists one more time and ask one single question. What single factor is going to make the biggest impact in energy reduction in the next 5 years from your perspective? And you have 3 words to answer. So I'm going to start with Jack.
From a technology end, still transistor basics, multi-gate structures.
Okay. Dan?
I think it's still going to be voltage.
Mm-hmm. Kyo?
Variation.
Variation. Mm-hmm. Okay. Philip?
Okay, so I'll cheat. I'll say sense and react because that's my theme, and then I also say planar or FDSOI.
Mm-hmm. Okay.
Radical circuit revisions and protocols.
Okay, great. Hermann?
Architectures, algorithms, and use profiling.
All right. Thank you. So this concludes this panel. I believe that you've heard a very interesting overview and set of ideas on what we can do to reduce power over the next 10 years. I really would like to thank all panelists, the domain experts, and all of you in the audience.